Section 4.5 problems. The first problem we discussed earlier in the PowerPoint slide. The model, the population model for Africa, was shown to be A equals 807 times E to the 0.024 t. So this was our model for the population of Africa. The question that we did not answer earlier in the PowerPoint slide is this one right here. By which year will Africa's population reach 2,000 million or 2 billion? Okay, so in other words, it's asking us, find t so that the population A is 2,000. Now we have to use 2,000 because this population model here is given in millions. So this is 2,000 million. Yes, it's 2 billion, but we have to use the value in millions. So to do that, we will let A be 2,000. So 2,000 equals 807 E to the 0.024 t, and we've got to solve for t. Okay. Now we do this in the same way that we did before in the PowerPoint slide. First, you have to isolate the exponential here. So we'll divide both sides by 807. So 2,000 divided by 807 is equal to e to the 0.024 t. Then, to get the t down here on the ground where we can access it and solve for it, we'll take the logarithm of both sides. So we'll do that. So the log of 2,000 divided by 807 equals the log of e to the 0.024 t. Okay. As before, we use the power property here on the right. So the left side for the moment is unchanged. Copy that down here. And on the right side, the power property applies, so 0.024 t times the natural log of e. The natural log of e is 1, and it goes away. So we now have t down on the ground and in a place where we can isolate it. Simply divide both sides by 0.024 so that we have the natural log of 2,000 divided by 807. That quantity, all divided by 0.024, that will be our value for t. And that will give us an approximate value of t of 37.8 years. Remember, this is measuring time since the year 2000, so this is years since 2000, or in other words, approximately the year 2038. And approximately that year, the population of Africa, according to this exponential model, if the percent rate of growth stays the same, would reach 2 billion people. Problem number 2. This was the learning theory logistic function as discussed in the PowerPoint slide, but we have two different questions here that were not addressed earlier. So the first question, find the proportion of correct responses after 10 learning trials. Okay, so that would mean that t is equal to 10, and we wish to find f of 10. So we'll take our logistic model and we'll substitute in the value of 10 for t, 1 plus e to the power negative 0.2 times 10. Okay, and then we'll work that out a little bit and we will get approximately 70.46, or in other words, approximately 70.5% will be the proportion of correct answers after 10 learning trials. Remember, the initial amount was given to be only 40%. So after 10 learning trials, the learning taking place has increased dramatically because most logistic functions, as we mentioned, start out with a period of very rapid rise. In fact, it's an exponential rise. And then after a very specific point, they begin to increase, but less and less and less rapidly. So we started out with 40% correct, and now after some period of time, we're at 70.5%. Let's take a look at the next question. What is the limiting size of f of t? In other words, what is the value here that the function will approach when t, the number of trials, becomes very, very large? So mathematically, this is asking us to find the limiting value as the number of trials becomes larger and larger and larger of the function f of t. Okay, how do we do that? Okay, let's write down f of t here off to the side. So f of t was 0.8 divided by 1 plus e to the negative 0.2t. Okay, now, as t becomes really, really large, this exponential here becomes very, very large because t is growing, but the exponent here is negative. So this is a very large number for the exponent, but negative. So what that means is, as t gets larger and larger and larger, you'll have 0.8 divided by 1 plus e to the negative large. Well, a negative large exponent, by rules of exponents, we could rewrite that to be 0.8 divided by 1 plus 1 over e to the positive large. It's by rule of exponents. And this quantity right here is going to approach the value of 0. The larger the exponent becomes, the larger the denominator becomes, and 1 over very, very large shrinks to 0. So the entire fraction reduces to 0.8 divided by 1 plus 0, or 0.8. 0.8 means 80%. So about the best we can do over successive continued learning trials is to have a 80% proportion of correct answers. So it means here on the graph, our limiting value is about 0.8, or 80%, which is a doubling of where we were from the original. Let's take a look at the next problem. This is the table, as discussed in the PowerPoint slide, of showing various walking speeds of people. And we plotted the graph in the PowerPoint. And what we found, we got the walking speed here as a function of the population here. And we found that there's a rapid rise followed by a leveling off. So this is typical logarithmic in nature. Now, how do you know if you want a log function or a logistic function? Well, as I mentioned, logistic functions tend to have an S kind of shape. So these are more logistic in nature. Whereas log functions tend to have this concave down, increasing but by less and less and less. And this is typical of logarithmic types. So I actually tried to model this on the calculator and asked for both a logistic model and a logarithmic model, and it gave me each. And the logistic model, sure enough, curves this way and then attempts to come back. So the fit is not really that great. The log model, though, was an excellent fit. The log model overlaid the sequence of points quite accurately. In fact, I'll tell you what that log model was. So the log model that I found that worked the best was 0.04 4413 plus 0.388365 natural log of x. So this is a type of function called a plus b natural log x. Okay, so the a lifts the curve up from here to here to here to here to here. That's a lift. And the b is a multiplier, which allows the logarithmic curve, which is generally shaped like this, to stretch a little bit. And these are the correct values of a and b that makes the data fit quite well. And when you try to do that on the calculator, you get quite a nice fit. In fact, it looks about like that with this model right here. So typical log type model would be most appropriate for this particular data. Now, under what conditions would a logistic model work out? Okay, well, logistic models are very good for biological processes, so often population growth, particularly if the population is on, say, an island with limited resources, then what you find is that with a lot of resources in the beginning, the population goes through a bit of an explosion, and after some critical juncture, the population still grows, but the competition for those resources starts to limit the growth of that population. So often you have population on this axis and time on this axis. It also works well for spread of disease, such as colds and viruses. And there are other applications for logistic models, but the competing factor here with the logarithmic function is that we have this magic place here where the growth begins to become less and limited. And prior to that, it's a growth explosion. So they're generally S kind of shape. So if your data here is more of that shape, where your data shows some growth here, and then after some point begins to level off like that, then that would be more typical of a logistic type growth model like that. And we would assume that there's a limiting value here. Log models can have limiting values too, but they're not S-shaped curves. Let's go on to the last question here, number 4. This is different, and this is asking, rewrite, here's the function, 4 times 7.8 to the x. There's an exponential model. So the 4 right there represents the initial amount. And we say the initial amount because that's when the variable is 0. 7.8 to the 0 power is 1, and 1 times 4 would be 4. And then this is the factor here which makes it grow. And in fact, if this growth factor here is larger than 1, that's what represents growth. And a fractional quantity here would represent a decay or a decreasing curve. Okay, what does the question ask? Write this function in terms of base e. So in other words, we want to transform this into a function that has an initial amount, we could call that a, times e exponential to the k times t. Okay, so there's base e exponential. Okay, so generally this represents continuous growth, whereas often this here represents discrete growth. In other words, it's growth per unit time. means discrete, whereas this is growing all the time for all values of t. Turns out we can turn one into the other and vice versa. Okay, how do we do it? Well, what we're saying here is that we want 4 times 7.8 to the x to be equal to a times e to the kt. We want these two models to be exactly equal. Well, in order for these models to be equal, the multiplier has to be the same. So a must be 4. We have no choice there. So the a is taken care of. In other words, 4 times 7.8 to the x must be equal to 4e to the kt. Okay? And we can divide both sides by 4 and eliminate that quantity. So what this boils down to is that 7.8 to the x must equal e to the k times t. Okay. Sorry, I'm using t and x in the same. See, if our original here is x, we want this to be x. The variable has to be the same, which means we want this to be an x, which means we want this to be an x. So here it's an x. The variable is either x or t, whatever it is, it must be the same everywhere. So it represents the same type of quantity. Okay, well, we could view it like this. 7.8 to the x. Now shift this in terms of a rule of exponents. And we could write this as e to the k all to the power x, because power to power will multiply, giving you k times x. Now, since both expressions have exponent of x, then these bases must be the same. So therefore, 7.8 must equal e to the k. This is what it boils down to after discovering that the initial amount must be the same, the variable must be the same, so at the heart of it, the base here must equal the base here. So solving for k, we take the natural log of both sides, natural log e to the k, and use the power property on the right. So the log of 7.8 is k times log e, and of course log e is 1, so this is just k. So the exact value is original exponential is same, and I mean exactly the same as y equals 4e to the natural log of 7.8 times x. So these are exactly the same, or we could say approximately our new model is y equals 4e, take log of 7.8 on the calculator, which is approximately 2.054 x. So here's the approximation, and this is the exact version of this. This is our discrete exponential. This is our continuous e exponential. That concludes problem set for section 4.5.